Hey guys, what is up? This is Team RoboBoat. I'm Mia.
I'm Yuva.
Sohyun, Bella,
Shirley.
and this is
RoboBoat! Our motivation comes from the limitations in the previous RoboBoat system, which relied solely on a camera for navigation. Since cameras provide only 2D information and are sensitive to lighting, we integrate LiDAR for precise depth information and a more robust navigation system. We evaluate our approach through the follow the path task. For this task, the boat must autonomously navigate through a path outlined by red and green buoys. The camera component provides the boat with vision, and the LiDAR component provides the boat with depth information, which together allow the boat to have a 3D vision of its environment.
Now, let's go over our hardware components. Our boat consists of 4 T200 thrusters for motors. At the front, we have MID360 Livebox for LiDAR with Oak-D LR camera on the top. In the electric box, we have switch for the main power, power cable to the LiDAR, and electric speed controller. On the right half, we have the Arduino and Justin connected to the camera and LiDAR.
Three main goals we wanted to achieve were to train a fast and reliable buoy detection model, to implement sensor fusion by mapping LiDAR points onto the bounding boxes around buoys generated by the buoy detection model, and to improve the path planning algorithm by taking the new LiDAR depth data into account. First, to train a reliable buoy detection model, we used this buoy dataset of 15,000 images by MHSeals on RoboFlow. They conveniently had a GitHub repository with the script to train the model on this dataset. Once we trained the model, we needed to set up ROS2 nodes for gathering camera data and running inference. Our initial ROS2 architectures included getting raw data from the camera and running inference on the onboard Jetson. However, we later figured out that offloading inference to the camera resulted in faster inference and faster publishing of the coordinates of bounding boxes to be used in sensor fusion.
For our second goal, first we want to obtain the extrinsic data to map the LiDAR points to the image we collect. This is done by the MATLAB LiDAR and camera calibration tool, which uses the dataset we collected of paired images and LiDAR points with a checkerboard in C. Given the XYZ coordinates of the points relative to the sensor, we can calculate the depth of each point from the LiDAR sensor or the boat. Now that we have our mapped LiDAR points, along with the bounding boxes we obtained from the detection model, we can estimate the relative distance of the detected buoys through the depths of the LiDAR points in the boxes. We have tried averaging the depth of all LiDAR points in the bounding boxes or use the closest point in the box. After some tests, we find that using the closest point allowed us to obtain more accurate results as it takes the least impact from the error in the calibration.
Our third goal was to improve the path planning algorithm. Previously, our path planning relied only on the camera input, which gave us 2D image coordinates. We used the most recent red and green buoy detections to draw a path and calculate the midpoint X to steer the boat. While this worked in simple cases, it had major limitations such as there was no depth information, so the algorithm couldn't tell whether a buoy was near or far, leading to occasional steering errors.
Colliding.
To solve this, we introduced a depth-aware system by fusing YOLO detection with depth data. Now we select the closest buoy as reference points, which improves accuracy and avoids reacting to far or irrelevant objects. This upgrade gives the boat a more 3D-aware sense of its environment and results in much smoother navigation.
Here's a visualization of our system. As you can see on the right, the boat selects the closest red and green buoys as references, marked by bounding boxes filled with color. It then computes the midpoint using the references, shown as the yellow line, and steers left or right based on the threshold. We experimented 10 consecutive runs to test the robustness of our system. In total, we were able to achieve 7 successful runs, 2 fails due to collisions, and 1 going off track.
Our accomplishments for this quarter included completing our MVP, and our MVP was to complete the follow the path task through using camera LiDAR sensor fusion. And we also had some extra time on our hands, so we began to prototype the odometry and basic mapping system, which uses GPS and IMU. Visuals of what that looks like are shown below.